Okay, well, let's jump into really the third component of connection design, which is really what are the connected elements doing? So we've looked at bolt strength and we've looked at weld strength. Now let's look at what happens in the material, plate usually, or angle, what's going on in those. So let's jump in here. So failure mode, there's a variety which actually very closely parallel the failure modes we've already been looking at in members. We can now apply basically those same concepts to the connected elements of a connection, the little plate angle bits. So failure modes in tension, we have net rupture and gross yield. Shear, block shear is kind of the new one where you have a hunk of the material that rips out, a portion fails in tension, and a portion fails in shear. We'll focus on that for this PowerPoint. We also can have compression. Say this brace was pushing this way. If this distance here is long enough, this portion can buckle. The way this joint's configured, it would be pretty hard to buckle, but sometimes they can. Okay, so the general equations, tension yielding, tension rupture, direct shear, and then block shear we'll get into. This Burley connection here was designed pretty much off of these equations. So it basically taking the brace force, creating resultants, tension and shear resultants in the joint, and then just working through piece by piece um, each design element. So in the end, a joint like this, it looks fairly complex, can be designed with just, like eating an elephant one little bite at a time until you get through it. Okay, so for block shear, like I said earlier, we have a portion that fails in tension and then a portion failed in shear. So we have the capacity is equal to the minimum of two different strength types. So the first equation is a shear rupture, which is given by this term. The second term is a tension rupture, but you'll see these two stay the same. And then in the shear yield equation, this portion here changes from rupture to yielding. The definitions are all here. UBS is a shear lag factor. So if we look at this figure from the commentary in the spec, you can see cases where UBS is 1, which generally tend to be single rows of bolts or double in a gusset, or UBS is 0.5, in this case at the end of a beam with a double column of bolts. Now keep in mind this doesn't mean the connection strength is half, it just means this component of the connection strength counts for half. So it doesn't tend to be the end of the world, it just is a slight reduction. So anyway, what I like to do is calculate each of these three terms separately and then put them together in the equation, see which one is the smallest, hit that by 0.75, and that's my block shear strength. Generally speaking, if you use plate thicknesses that play nicely with bolt sizes, things tend to work out just fine in block shear. So like 3/4 inch bolts tend to play nice with 3/8 gussets. 1-inch bolts, maybe 3 or ½ inch to maybe a 3/4 gusset. Just depends on the geometry. So you can play around with that and see what makes sense for you. Okay, if we have a joint that has a fair amount of, well, if it joint's in compression and it's fairly slender, say the gusset is slender, so if I took this image here and said the whatever restrains the end of this plate is quite a ways away, we could get buckling in this region due to that. So if I were to come to these equations, if my slenderness is less than 25, I can just use this area times yield. So basically no buckling. If it's greater than 25, then we can use the column chapter equations to calculate things. Ideally, if this is new design, we have the ability to configure our joint so things aren't going to buckle. So I may choose to move that interface up here so my buckling length was less, thereby meeting this L over R criteria of less than 25. Okay, so some examples of connections. Here is a horizontal brace. So this brace would be running in a horizontal plane. We use these a lot in industrial facilities to create truss diaphragms. Anyway, this brace can bolt to this side, weld to this. There's a note saying somewhere here, let's see. Oh yeah, you can bolt to both sides if you want. That's a pretty common question. And then based on different marks, so sometimes when I do connection design, I'll actually be a little more specific on the plans, which brace connection to use. There's a schedule here that identifies how many braces or bolts in the brace, how many bolts here, size of weld, length of weld, etc. Here's a little more in-depth example of a beam into a column web. Heavy brace, this is known as a claw connection, where there's 4 of these angles that bolt to the flanges of the brace and then bolt into the gusset. And if you remember from our tension rupture design discussion the other day, quite a while ago actually, if I don't connect this here, I have to apply a shear lag factor to this joint, which is basically going to just increase the forces of the joint or decrease the strength a little bit. All right, so that's that. Kind of 2 primary heavy connection, or I guess heavy connection here, lighter connection there. And with that said, let's look at the example that I've given you. So I've taken this brace here and designed a handful of things. The first one is I sized the number of bolts required here just to get a feel for the geometry. That's a good place to start based on the force. And then I designed this gusset plate, and then the weld here, the bolts here, and the plate here. So the bolts are all things you've designed before, but I show you them in this example. And then the yielding across here, and actually I did a shear or block shear calculation of this hunk right here. So I'm just kind of walking through this. I start off with a 34 kip brace force. That force would come from an analysis model or my hand calculations. And then I've got, I take my bolt strength and shear, divide that into my force, and I get 1.9 bolts. I like to match the number of bolts to the angle leg size. So if this is a 3-inch leg, I like to use at least 3, 4-inch leg, 4, etc. Anyways, so and then next I check bolt bearing and find that I'm totally fine with 2 bolts, but I'm going to still keep it with 3. Then I jump into the gusset. So I need to find the tensile area at the last bolt hole. So that's this dashed line, and there's a theory called Whitmore stress block, which says the forces will transmit at about 30 degrees from the axis of the force. So that's where I use that 30, pull the dimension in CAD 13.2, multiply that by the thickness of the material. I get close to 5 square inches, hole reduction, and then kind of work my way through the tension rupture and the tension yielding strength equations, which, as you can see here, are both quite a bit higher than the actual force. So you might argue, well, why don't you go down to a 1/4-inch gusset plate? I could do that, but generally I just like to start at 3/8 gussets. All right, next I do the block shear calc. So there's this rupture area along here, a tension rupture across the top. So here are my two equations. I find my parameters, I find my areas, just one little thing at a time. So the net shear area is going to be this length minus 2.5 bolt holes, because we've got 1 bolt, 2 bolts, and we go to the center of this hole, so just half a bolt is reducing the length of that material. Run those numbers, I get just over 2 square inches. The gross is just my 8 inches times 3/8, which is 3, conveniently. And then my net tension area is from the edge of the hole here to the edge of the angle. This number here comes from the Stihl manual. It's the standard gauge on an angle. And on the next page, I calculate those two shear rupture, shear yield terms, tension rupture, run those numbers together, 83 kips or so, phi factor, 62 kips, greater than the 34 kips of tension. You'll notice I don't like to rewrite the force. That way, if things change, I can just in one place be calling out the force to compare everything to. All right, the next part of this is finding the forces at the interfaces of the gussets. So knowing what this force and the force here, and it occurs to me I don't really have a great image of all of that. Let me pull one up really quick. Okay, so this is out of the Stihl manual. So this is the image we were just looking at. We want to then find what are the forces, shear and tension at these two interfaces. So I'll go and toss that into the example. But that's kind of what we're aiming for here next. So this is there should be a reference somewhere. Where did things go? Hang on. Anyway, there's a reference here. So page 13-3 of the manual walks you through this. It's fantastic. Anyway, so on the next page, well, basically, if I kind of the crux of all of this is if I take these two sides of the equation and they're equal, there will be no moment in this connection, and that's good. And a lot of structural engineers kind of see that as important. I think it's less important because a lot of times those moments aren't all that big. But when we're configuring this, what we try to do is choose this beta and this alpha, so this equation are equal to each other. So that's what this next portion on the next page. So I use these in my connection projects quite a bit. So I've got this kind of programmed in here that I can solve these two, set them to 0. So in this case, what I did is say this beta is defined as 5.5 inches. So 3 plus 1.25 inches plus 1 inch roughly. And then my EC, which is from the center line to the face, and B, or what is that? Remind myself here. This EB term goes from this gusset interface to the center line of the beam. So that dimension are given by the choices of members. This one I chose, which just leaves one variable in this equation right here. And so I use goal seek to set that equal to 0, which is just those subtracted from each other. And then I goal seek on that alpha term to get this to be a no moment situation. And then these VC, HC, HB, VB are those interface forces. Okay, so I pulled those into the example. So basically we have at each interface where the gusset touches either the beam or the column, we have the forces for those. Typically we weld to the beam, so the beam comes out with a gusset on. We bolt to the column. That's far easier than trying to swing the beam in. Plus column flanges tend to be fatter, so they're easier to bolt to. Okay, so on this next page, these are basically the hand calcs that validate these numbers. And then at the end of the day, I say, okay, I want to design the weld at the beam. So basically this interface. And for a fillet weld, I'm going to say the weld is in shear. And so I'm going to look for a resultant of those two forces. So I come here and find the resultant, which is just the square root of the sum of the squares, 20 kips. Here's the weld calc. You'll see I have 165 kips of strength and only need 20. So that joint's plenty strong. And it might not hurt to back this off on the capacity a little bit. Next step, I look at the bolts of the column. So similar, I find the resultant because I'm going to say whatever vertical force and horizontal force going through those bolts really can be treated as a resultant at an angle. In this case, the angle is irrelevant. What is relevant is this magnitude of resultant, 14 kips, which is really close to the strength of a single bolt. I have 3 in there, so we've got 53 kips. So kind of what I'm seeing here based on the calcs is if I wanted to back this off, I could probably go to 1/4 inch plate, go to 1/4 inch plate here, 2 bolts, and that would, if this shortened vertically, this would pull in here. Probably could go to 2 bolts here. Um, However, for me, I would rather just err on the side of a little stronger in connections, mainly because I'm not interested in a connection failing. I would rather have the member fail. Okay, so that's this size of the bolts. You can see it's quite a bit bigger. And then the next interface I look at is this plate here. And there's 2 ways to do this. I could design this plate in tension for the component of force horizontally and that plate in shear, and then try to find some equation in the code that would give me the tension shear interaction. I don't know that I know of one. The next option would be to just say, all right, I'm going to design this plate in shear for that full resultant. It's a little not technically perfectly correct, but what you'll see here when I did that is I end up with 57 kips of capacity and only 14 kips of demand. So at the end of the day, my connection just in shear is quite a bit stronger than my demand. So whatever nuances I might be off by not looking at the 2-directional components, I'm not really worried about it given how much shear strength I have. And I could similarly do that in tension, although those numbers would come out higher than this one. So that's why I chose the shear. All right, with that said, I'll leave it to you guys to start looking at your connected elements and your trusses you're designing, and hopefully this gives you a good start on that.